Discontinuity, section 1.5. So we're going to start out with the definition of continuous function. So I'm going to let f be a function defined on some open interval that has c on the interval. And there's two things. One, f is continuous at c if the limit as x approaches c of f of x equals the function output f of c. Okay. And then two, f is continuous on the interval I if f is continuous at c for all values in I. Okay. So not only is it continuous at one point, it's continuous at every point on the interval, then it's continuous on that interval. And if f is continuous on negative infinity to infinity, then we say that f is continuous everywhere. Okay, so an idea, a way to think about continuity in a simple layman's terms, informally, a continuous function is one that you can draw without picking up your pencil. Okay, so as long as you don't pick up your pencil when you draw it, theoretically, I mean, that's continuous. That's the idea. So you can draw this curve without picking up your pen or pencil. It's continuous. Okay, here I can draw and then I have to pick up my pencil and come back and then draw the rest. There's a discontinuity going on there. That's the simplest way of thinking about it. Okay, can you draw the curve without picking up your pencil? Even if it is for one single little dot that you have to pick up your pencil to get over the dot. Okay, so the next question is, how do you prove that f is continuous at a point C? So we're only talking about proving it at a single point. Okay, so is it continuous at that one point? Yes or no kind of thing. So there's three things that must be true. So here's thing number one. Number one, okay, so if you're asked to prove that a function is continuous at a single point, this is what I'm asking for you. I want to show that the limit as x goes to c of f of x even exists, okay? So how do I show that a limit exists? Think about this. I have to show that the left-hand limit, right, is equal to the right-hand limit, okay? And if the left and right-hand limits are equal to each other, then that proves that the limit exists, okay? Now, I'm not saying what does a limit equal, I'm just saying that it exists, okay? Existence is different than saying what it equals. I'm just saying that it's possible to find the limit, all right? So that's number one, it exists. Number two, not only does the limit exist, but if I plug in c at the function value, it's defined, okay? So there's no undefined thing. It actually outputs some number. It's defined, so there's no hole there, okay? So it's not missing a hole. It's actually defined at that point. The last one, number three, is that not only does the limit exist and f of c is defined, but the limit as x approaches c of f of x is actually equal exactly to the defined f of c. And if this is the case, then what we can say is that the function f is continuous at the point c. Okay? So a little involved, but that's the three things that must be shown in order for it to be true. Okay? So one thing that's good when you're talking about showing something to be true continuity-wise, a good thing to do is kind of look at, well, what is the opposite of continuity? Well, that's discontinuity. So if we know all the reasons for discontinuity, you know, maybe it helps figuring out where it's continuous a little bit easier. We know all the things that we don't want to happen. Okay? So discontinuity at some single point x equal to c. So first reason, okay, this is opposite of number two. So instead of f being defined, f is not defined. So what does not defined look like, right? So one example of not being defined at c, okay, so you go to plug in c, but guess what? There's a hole there. Well, you might be saying, well, Mr. Clark, you said you could draw something that's continuous without picking up your pencil. Well, technically, when I'm drawing this curve, I have to stop here, pick up my pencil, and then draw on the other side. So technically, I am, let me do this in a color you can see a little better. So I am technically picking up my pencil, okay? Even though it's a very tiny little pickup, okay, only at that point, x equal to c, you are technically lifting up your pencil though, okay? And so what's going on here? There's what we call a hole at x equal to c. There's a hole in the graph. Now that hole could be the cause of something like if you had, some factoring going on. So maybe it's like an x minus c factor, and I have an x plus 2 or whatever, and then divided by x minus c factor or something like that, right? And so there's a hole there because those two factors canceled, okay? That could be one example of a hole. Now, another type where f is not defined is, say we have some vertical asymptote. With a vertical asymptote, we know that we will never cross vertical asymptotes. That's why I used red here. Okay, red I think of it kind of like a red light. You don't run red lights, otherwise you might die, right? So we don't cross the red line here, okay? Vertical asymptotes with polynomial functions, you're not going to cross the vertical asymptote. So it's not defined. There's nowhere you can plug in and get it, all right? So you have your asymptote at x equal to c, and it's caused by this vertical asymptote. The next reason for discontinuity is the opposite of reason number one. If the limit does not exist, okay, the limit does not exist. So what are some examples here? Well, an example of a limit that does not exist, you can see here we're coming up. If I do the finger method and I come down to C, my left and my right hand fingers do not pair up. Therefore, the limit doesn't exist because why? Well, the limit as x approaches c from the left is not equal to the limit as x approaches c from the right. So how do you show that limit does not exist? The easiest way to do it is to show that the left-hand limit and the right-hand limit do not equal the same thing. Left-hand limit here is equal to, looks like 3, and the right-hand limit is equal to 1, and 1 and 3 aren't equal to each other. Okay? But f of c, the function value, if I plug in c, it outputs 3. So it's defined, right? So check on this part here, okay? However, the limit does not exist, so it can't be equal to the function value. So the other two things fall apart, and that's why there's discontinuity going on there, okay? So what we do, we call this a jump discontinuity. Why do we call it a jump? Because we've got to jump to get to the rest of the curve. Okay, there's a jump between one part of the curve and the other part. So that's a jump discontinuity. Now, the third reason, okay, has to deal with the limit as x goes to c of f of x equal to the function value inputted at that, or the output at that point, okay? So instead of it being equal, the opposite of that is not being equal, all right? So you see how we're just taking the definition in its three parts and doing the opposite of that, okay? So we're negating it. Now, a limit as x goes to c of f of x is not equal. Okay, so what do I mean here? Well, if I do the finger thing and I run my fingers, my left and right hand together, it looks like I get a limit of 2. Okay, so that 2 is the output, the function value here. Now, the limit is equal to 2. However, if I plug in c, what happens? I get an output that's a little bit higher. The output looks like it's 3. Okay, so what do I know about 2 and 3? They're not equal to each other. okay? So since f is defined and the limit does exist, okay, so look, guys, we were really close here. The limit existed, f was defined here, but what was the thing that fell apart? The limit did not equal the function value. And so really you have to have all three of these, okay? So you got to have all three of these for this to work. All right, so the limit did not equal the function value, and therefore it's not continuous there. And looking at the picture, I mean, it's obvious. You can see it's like, well, yeah, I can't draw this one without picking up my pencil. I can't draw that without picking it up. I can't draw that without picking it up. Right? So, you know, it's an easy way to look at it, but just looking at it and saying, yeah, no, that's not continuous is different than saying, well, it's not continuous because the left and the right hand limit don't match up. They don't equal each other. Okay, so we have to be more precise in our wording. All right, we can't just be like, yeah, the limit doesn't exist. Tell me why the limit does not exist. Okay? Now, there's two discontinuities we're going to focus on, and one is the removable discontinuity, and the removable discontinuity is just a hole. Okay? So all you need to do to fix the discontinuity, and when I mean fix it, I mean take it from being discontinuous to now being a continuous at this x equal to c. So all you have to do to fix it is you have to make the limit equal to the output, okay? So which of these examples will be removable? Well, places where all you have to do is make the function output equal the limit value. This first one here, if I just make it defined at this value here, then voila, it's continuous at C. So that would be removable, okay? So, oops, sorry. So this would be an example of removable, okay? Removable discontinuity. Now, if I put a function value, I define it right there, or right there, right there, that's not going to fix the problem, okay? You cannot put in a function value here in this vertical asymptote part, and all of a sudden all your problems are wiped away. It's still, you're going to have to pick up your pencil at some point, okay, to fix the problem. All right. Now here, even if I make that an open circle, I mean, where am I going to put the dot so that it connects the jump, right? So that's a different type of discontinuity. Now this last one here, all I have to do is I just have to take this dot right here and move it down to here, and I've fixed it. So truly, these two situations are removable discontinuities, because only thing we had to do to fix it was to get rid of that not equal to by moving this dot down here, okay, making the 3 dot come down to the 2. All right, so that's the idea of removable discontinuity. So the other type is the non-removable. So non-removable means what? A jump or a vertical asymptote at x equal to c. Okay, so a vertical asymptote is non-removable. We can't fix that, okay? And the jump, we're having trouble. We can't really fix that jump discontinuity there either. Okay, so those are non-renewable, all right? So in this problem here, I'm going to let f be defined by the graph below. And so here's my graph below. And I'm going to give the intervals for which f is continuous. And if f is not continuous, then I'm going to state why it's discontinuous. So one thing I like to do, I like to just kind of draw with my pencil, okay, where I think it's continuous. And that's where I don't have to pick up my pencil, right? So from here to here, looks like to here, and then here, and then there, and then here, okay? And that arrow, it looks like it's going on forever and ever, right? Okay, so where is that coming from? It looks like from -10 to -7, and then -7 to -4, and then -4 to 2, and then from 2 to 4, 4 to 7, and then 7 to infinity, right? So how do we designate the interval? I'm going to use interval notation to write this. So my intervals, -10 to -7 right here, and then I don't jump, but I have a removable discontinuity, right? And then -7 to -4. And so you just need to connect all these with a bunch of unions like you did whenever you were in college algebra. 2 to 4, 4 to 7, and then 7 to infinity. Okay? So hopefully those colors kind of help you pair everything up. All right, so those are all the continuities. Let's focus now on the discontinuities. So the first discontinuity I see is at x equal to 10. Well, you might be like, well, look, it's defined there. But what do we know about continuity? Not only does it have to have a limit on the right, but it also has to have a limit on the left. Well, guess what? The function isn't defined on the left. So what do you know about the limit as x goes to -10? Well, if I use the finger trick, right, I can get the right side, but then the left side, it's like, well, it's not defined. Therefore, the limit does not exist. And if the limit does not exist, then that contradicts the first rule, which says that I have to show that the limit exists. Okay? Excuse me. All right, the next one is x equal to -7. -7 looks like a removable discontinuity. So this one here is not defined, all right, at f of -7. And since it's not defined there, then that contradicts rule number 2, being it has to be defined. And therefore, we can say that it's not continuous. Okay, it's a removable because all it takes is plugging in an f of 7 equal to the limit at that point, and then you've got a continuous at -7. All right, -4, that's the next issue. This one looks like a vertical asymptote, so that's non-removable. It's not defined here. Clearly, we don't have a point where if I try to plug in -4, I just get undefined or does not exist. That makes it discontinuous, and it's non-removable as a type of discontinuity. Okay, so not only are we stating, yeah, it's discontinuous, but I'm stating why it's discontinuous. So that's a big thing that I'm looking for here. Okay, so you need to make sure you understand all the points of this and ask me, through email or whatever, if you're having trouble understanding these different nuances. Okay, x equal to 2. Now with x equal to 2, all right, with x equal to 2 here, what's going on? Well, it looks like I have a vertical asymptote, but it's kind of a weird idea, right? So we got one vertical asymptote here, and typically you're used to seeing your other side of your graph come up or come down. But this isn't a polynomial. This is a piecewise defined function. It's defined in pieces, right? So it doesn't really play by the same rules that we're used to. So it is technically defined at 2, x equal to 2. So it doesn't break this rule. This rule's okay. However, the limit here does not exist. And why does it not exist? Well, I think that's pretty clear, right? The limit on the right side is 1. The limit on the left side, which we'll talk about infinite limits later, but for right now, we say it does not exist, okay? So that left and right hand limit don't line up, they don't equal each other, therefore the limit does not exist. And that's how you would state it. You don't just say does not exist, you tell me this left hand limit does not exist, but the right hand limit equals 1, therefore they don't equal each other, which causes this to not exist. Okay, it's non-removable, there's no dot that we can plug in that's going to fix everything. All right, x equal to 4. X equal to 4 here. So, we got an interesting thing going on here. It is defined, right? If I plug in 4, I get out 2, clearly, okay? But the left-hand limit looks like it equals 1, and the right-hand limit looks like it equals 3. So the left and the right-hand limit do not exist, or they don't equal the same thing, therefore the limit does not exist, okay? And I would say that this is non-renewable or non-removable, because even if I put a dot, just one dot somewhere, there's no way I can connect those two graphs, as you can see there, okay? It's non-removable. The last one here is the 7, x equal to 7. And with that one, with x equal to 7, looks like I just have a hole there. So that's definitely going to be removable. But why is it not continuous here? Well, clearly because it's the hole. And so the limit exists. The function is defined, right? So the first two things are good to go. The limit exists and the function is defined. However, the last thing, where the limit equals the function value, is where it falls apart. And so this is classical setup, okay, so contradicting number 3, which is the removable, okay, makes it a removable discontinuity, okay? All right, so in the next video, we're going to talk about one thing I want you to notice in all of these continuous intervals, they're all open intervals, okay? So how we have defined continuity is via an open interval, all right? So it's on an open interval. So in the next video, we're going to extend our definition from an open interval where we only have parentheses to closed intervals, and that's going to be more of a complete definition for you. But typically, most textbooks, they stick with just the open intervals. So if you go on to take higher math, this will suffice for you here, that you're continuous on this open interval, okay? All right, guys.